All right, today we are going to talk about exponential growth. And the idea here is that in many applications, as you can see, that the rate of change of a variable y is proportional to the value of y. All right, so if we just kind of think about this with some function that we would already know, let's say we have an exponential function. Okay, and what we can see here is that the value of y, as the value of y increases, then you can see that the rate of change, or the slope, also increases as well. It's proportional. If I draw tangent lines, you can see that as the y value gets bigger, the slopes of those tangent lines is also getting bigger. And so that's the idea. So how would we express that in a mathematical sentence? Well, we would say the rate of change of y, so how would we write that? dy dt is proportional to, so we need a k anytime we're saying proportional to, the value of y. And that is the idea for that first part. All right, so now in example 1, it says find the solution to this differential equation given that the initial condition is right here. Y is equal to y0 when t is 0. So that's what we want to do here. So we've seen these before. What you want to do is you want to separate the variables. And so we're going to say 1 over y dy is equal to k dt. And now we're going to integrate both sides. So we're going to integrate this left side, and we're going to get natural log of the absolute value of y. And we're going to integrate the right side, and we're going to get kt plus a constant. And then we're going to have to do this around the world thing. Hopefully you're pretty familiar with this because we've done this several times. We're going to rewrite this into logs. So that's going to give us e to the kt plus c equals y. And then we can break this up into e to the kt times e to the c equals y. And then we remember that e to the c is just a constant. So we can say c e to the kt equals y. And now they give us an initial condition. They say y equals y sub 0 when t is 0. So if we plug in 0 for t and y sub 0 for y, what do we get? We get c e to the k times 0 equals y of 0. So e to the 0 is just 1, so we see that c equals a y naught. So c equals y sub 0. Okay. So now if we go back and plug that in as we've been doing all along, we get a final answer of y equals, we're not going to write c, we're going to write y0 e to the kt. And that right there is the basic solution to an exponential equation. And you've seen this before in other classes. This right here is going to be your initial value, and this is going to be your constant of growth. All right, if it's negative, it's going to be a decay. If it's positive, it's going to be a growth, and that's going to be the solution to that differential equation. All right, let's see how this works in a real problem. All right, first thing you want to pay attention to, it says the rate of change of y is proportional to y. So as soon as you see that, that means you have the liberty, you have the right to use the equation that we just came up with. You don't have to derive it again. So you can already assume that y equals y naught, the initial value, e to the kt. The first part of this video is just to derive how did we get that. But as soon as they tell you that the rate of change of y is proportional to y, you can assume that. All right, so do you notice there's two things that we are missing here, the initial value and the constant of growth. We need to find those, and they're going to give you enough information where you can find that. Well, the first one's pretty obvious. It says here that when t is 0, y is 2. So there's your initial value right there. So we can already rewrite this to be y equals 2e to the kt. Now the other piece of information that they give you is when t is 2, y is 4. So if that is true, then we can use that information to get k. So let's see if we can plug that in. So y is 4 and 2e to the kt. Well, t is 2, so 2k. All right, we're going to divide by 2, and we're going to get 2 is equal to e to the 2k. And then we're going to take the natural log of both sides. And then we remember this property that when you have the natural log of e to something, the answer is just that exponent. And so we end up getting natural log of 2 is equal to 2k. So we're going to divide by 2, and we get k to equal the natural log of 2 over 2. All right, so that is your k value. And you're going to want to leave it in that form right now until later when we're going to get a decimal as an answer. But for now, we will leave it as natural log of 2 over 2. So now we're going to plug that back in. So we're going to have y equals 2e to the natural log of 2 over 2 times t. All right, and then it says, what is the value of y when t is 3? Well, at this point, we just need to plug in 3 for t. So you're going to have y is equal to 2e to the natural log of 2 over 2 times 3. And at this point, you can plug this into your calculator, and you're going to get a value of approximately 5.656. And that is the answer to this problem. All right, with any study of exponential functions, exponential growth and decay, there's going to be a half-life problem, and so that's what we have here. Let's talk about half-life. Half-life is the amount of time that it takes for a substance to lose half of its mass. So it is the amount of time that it takes for a substance to lose half of what it started with, okay? So if, let's just say, our initial amount is y, 0, then what we are looking for, so we'll say that is our initial, okay, our initial amount. What we are looking for is the time, question mark, where y is going to equal half of what it started with. Okay, so that's what we're looking for. And it says in this problem, show that the half-life depends only on k. So what we're going to do is we are going to plug in 1/2 y0 for y into this equation right there. So we're going to say 1/2 y0 is equal to the initial amount, e to the negative kt. You may say, well, why is it negative? Well, because this is an exponential decay problem, all right, and we need to make sure that the growth constant is negative. So we are going to solve this for t, and we can see that y0 is the same on both sides, so that goes away. So we have 0.5 is equal to e to the negative kt. And then, just like we did in the last problem, we're going to take the natural log of both sides. All right, when we do that, we're going to end up with the natural log of 0.5 is equal to negative kt. And then we're looking for t, so we're going to divide by negative k. Divide by negative k. And this is going to cancel. And so what we're going to have is t is equal to the natural log of 1/2, and yeah, I don't know why I went from 1/2 to 0.5 back to 1/2, but you'll see why in a moment, over negative k. And so then next what I'm going to do is I'm going to take this negative sign and move it to the top of that fraction, and so that way we have t is equal to negative natural log of 1/2 over k. And then I'm going to apply this property of logs that is called the power rule. That says I can take any coefficient in front of a log and move it to be an exponent. So this is really going to be natural log of 1/2 to the negative 1 over k. And that's equal to t. And so when you're raising a fraction to a negative exponent, that just means to flip it. So your final answer is t, which is the half-life. That's equal to the natural log of 2 over k. And that is how you prove that the half-life depends only on the variable or on the constant k. Alright, we've seen this problem before in pre-cal, but we did not solve it using calculus at that time because we didn't know calculus. So, Newton's law of cooling. This is basically a simple law that says that an object will cool to the temperature of its surroundings. Wow, that's a major discovery, right? So, for example, if you take a pizza out of an oven that has an initial temperature of 350, so the pizza's hot, just came out of the oven, and you put it in a room that is 75 degrees, eventually the pizza will cool to 75 degrees. Wow, Newton got a law named after him for basically recognizing that. Pretty obvious. However, example 4, it says, if T is the temperature of the object at any time T, and T sub S is the surrounding temperature, the ambient temperature, the room temperature, then the rate of change of temperature is equal to negative K T minus Ts. Solve the differential equation assuming, now here is your initial condition right there. Excuse me, your initial condition, alright, is right there. Assuming that T sub 0 is the temperature at time T equals 0. So we need to solve this differential equation. Okay, so we are going to solve it the same way that we did before. We are going to get all of the capital T's on the left and all the little t on the right. So that's going to give us dt. Actually, you know what? Let me make that capital so we don't get confused. dt over capital T minus Ts, and that's equal to negative K dt. Because remember, little t is time, capital T is temperature, so we don't want to get those confused. Alright, so we're going to integrate both sides with respect to those letters. And if we integrate the left side, that's going to give us natural log, the absolute value of capital T minus Ts. Now, let's make sure we don't get confused. Ts is a constant, right? The room temperature is just a constant. It's set at 75. It's the thermostat is set at 75. Okay? What is changing is T. That is your variable. The temperature of the pizza is cooling down, so that is why that is your variable, because the temperature of the pizza is cooling down. It's changing. The temperature of the room is never changing. That's a constant. So you want to think of that as a constant. All right? So we're going to integrate the right side, and that's just going to be negative kt, little t, plus a constant. And then from there, we're going to have to do this around the world thing again. So we've seen this like 100 times, right? So this is going to be, if this is E, it's going to be E to that equals that. So it's going to be capital T minus the room temperature is equal to E to the negative K little t plus C. And then same thing before, we're going to have to break this up into E to the negative kt times E to the C. And then we remember that this is just a constant. All right, so we can just call that capital C E to the kt. So what we're going to have, let me move that up here, that's going to be T minus the room temperature is equal to c e to the negative kt. And then from here, we can use our initial condition to get capital C, and that says that when time is 0, t is t sub 0. So we're going to plug in right here, we're going to plug in capital T of 0, and we're going to plug in 0 for our time, e to the negative k times 0. All right, and 0 times anything is 0, so e to the 0 is 1, so c is simply t0 minus ts. All right, so if we go back and plug that into, so let me circle that, take that and plug that in there, and we end up getting an equation for Newton's law of cooling, which is T minus Ts equals T sub 0 minus Ts, all of that in parentheses, times e to the negative kt. And if we're going to add Ts to both sides, our final answer is really going to be capital T equals Ts plus T sub 0 minus Ts, and these are all capital T's, e to the negative k little t for time. And that is the equation that we're going to use in the next problem for Newton's law of cooling. All right, example 4. This is kind of a morbid question. A detective finds a murder victim at 9 a.m. All right, the temperature of the body is measured at 90.3 degrees Fahrenheit. So that right there, they are giving you the initial temperature of the body. So when he finds the body, that is the temperature of the body. All right, and then 1 hour later, the temperature of the body is 89 degrees. And the temperature of the room has been maintained at a constant temperature of 68. So maybe we need to start writing things down. So our initial temperature, T sub 0, is 90.3. And the room temperature, T sub S, is 68 degrees. All right. And then we see that 1 hour later, so our ordered pair is going to be 1 hour later. The temperature of the body is 89. So that's going to be our ordered pair that we're going to use. All right. And then it says, assuming that the temperature T obeys Newton's law of cooling. So what does that mean? That means we have the liberty to use this formula, T, and we'll just say, we'll make it a function notation. T of T is equal to the ambient temperature, T sub S, plus the initial temperature minus the ambient temperature, e to the negative kt. All right, we have the liberty to use that formula. All right, so assuming that, estimate the time when the murder occurred. Okay, so when the murder occurred, we're assuming that the body is going to be at the normal temperature of a body, which is 98.6 degrees, and we'll come back to that a little bit later. All right, so first thing we have to do here is we got to find K. All right, we've got to find K. So we're going to plug in everything that we know. All right, we're going to plug in 89 right here. We're going to plug in 68 right there. And we're going to plug in, well, the difference between 90.3 and 68 is going to be 22.3. So I don't need that right there. So 22.3 e to the negative kt. But t is 1 hour because of this initial condition right there. Not initial condition, but that condition there. All right, so we're going to solve this out. And we get 21 equals 22.3 e to the negative kt, or excuse me, negative k. and you end up working all of that down, and you end up getting a K value. I know you guys can do that on your own, which is equal to the natural log of 22.3 over 21. Okay, so that is your K, and I'm not going to make that a decimal for now because I want to get the most exact answer I can. So that is your K. So you're going to take that and you're going to plug it into the Newton's law of cooling. And now we're going to, look what it says, we need to find the time, estimate the time when the murder occurred. So we're looking for little t now. All right, so we need to go back, and now we need to plug in 98.6 degrees for the temperature of the body, and that's going to equal the same thing. It's going to be 68. Okay, we're using the same formula as before, plus the difference between them, so it's going to be 22.3, no different, and that's going to be e to the negative k, which is going to be the natural log of 22.3 over 21 times t. All right, and sorry I'm running out of space a little bit here, and so you go through that same process of solving for t, and I know you guys can do that right there, so I'm just going to skip straight to the answer. T ends up being negative 5.267 hours. Okay, and so if you convert that into minutes, that's going to be 5 hours and 16 minutes before 9 a.m. because that's when the guy found the body. So before 9 a.m. So if you subtract all of that, that is going to be 3:43 a.m. is the time when the body died. That's a cool problem. All right, guys. See you in class tomorrow.